Recently in one of my weekly live stream videos, I went over a kind of long multi-part problem. And one of the parts to that problem was finding intervals of concavity and inflection points in a given function. And I thought you might find it helpful to get a little bit more info on that topic. So that's what we're going to be going over in this video, how to find intervals of concavity and inflection points of a function. We are going to be kind of jumping into the middle of this problem because the clip that I'm going to show you in this video did actually come directly from that live stream video. And I'm just going to be showing you the section about concavity and inflection points. If you do want to see the prior parts that kind of got us up to this point, I'll put an info card up there so you can go check that out. And then you can come back and see the kind of conclusion of this problem here. Or you can just go back and watch that full live stream video if you just want to see the whole problem from start to finish. I'll go ahead and put that video right up there. But without further ado, let's go ahead and jump into the problem, and I'll show you how you can use the second derivative of a function to find intervals of concavity and inflection points. Now, moving on to part C here, we need to find the intervals of concavity and inflection points. So this is really not going to be too different from what we had to do for part A. Finding intervals of concavity is very similar to finding intervals of increasing or decreasing. Finding inflection points is very similar to finding critical numbers. Of course, part A didn't tell us to find critical numbers, but we had to find them in order to find the increasing and decreasing intervals. In order to find inflection points, we're going to need to do effectively the same stuff we had to do for this up here, except we're going to do it using the second derivative instead of the first derivative. Let's start by, let me just write down our second derivative down lower. So the second derivative of this function is f double prime equals negative 6x. To find inflection points, if you already know the second derivative of your function, in order to find inflection points, it's very similar to finding critical numbers. You want to be careful of where your second derivative equals 0. So we're going to look for places where the second derivative of our function equals 0. You would also want to be careful of considering where your second derivative does not exist. In this case, like I said, our original function f of x, our first derivative f prime, and our second derivative f double prime, all three of these functions are polynomials, meaning that all three of them are going to exist for all x values. So as a result, we don't need to worry about where our second derivative does not exist, but we do need to worry about where does our second derivative equal 0. Okay, so to do that, what we would have to do is take our second derivative and set it equal to 0 and solve for x. In this case, it's going to be pretty straightforward. If we divide both sides by negative 6, we just get x equals 0 is our only inflection point. So that's part of part C right there. Our inflection point is x equals 0. Okay, so what that tells you is very similar to what our critical number told us up here. What it tells us is that if we take a number line from negative infinity to positive infinity, and in this case we're using negative infinity to positive infinity because our original function f of x is defined for all x values. If we had a limited domain on this f of x, we wouldn't want to use all numbers. We would want to basically cross off whatever sections of our domain are not going to work. In other words, we only want to look at the x values that are a part of the domain of our original function f of x. In this case, that is going to be all real numbers. So our number line is going to be from negative infinity to positive infinity. And then the only point that we want to put on our number line is our inflection point. So now, very similar to what we had to do with increasing and decreasing, you can see that that basically split our number line from all real numbers into two different intervals here. Okay, so I like to, again, just write those intervals down. We have now from negative infinity up to 0, and from 0 up to positive infinity. And again, these intervals should not include your inflection point, because the inflection point is the place where your function does not have any concavity. It's switching from concave up to concave down potentially, but it doesn't, that one specific point, x equals 0, does not actually have any concavity to it. You can kind of think of it as like a tiny little piece of your function that's like going in an actual straight line. concavity basically just means curvature. So this point where it switches from curving upward to curving downward, or vice versa, that one little point where it actually switches from one to the other does not have any curvature to it. So we don't want to include our inflection point within these intervals. Now what we want to do is we're going to take, again, some number within these intervals. Doesn't really matter what number you pick. Let's just say -1 and +1. And we want to plug those numbers into our second derivative. I'm sorry, our second derivative is here. So we're going to take -1 and +1 and plug them into f double prime. If this is making sense so far, do me a favor and drop a comment down below. Just say got it so far so I know you're following along. And if you are getting some value out of this video, go ahead and just hit that like button too while you're down there, please. Be a huge help to my channel so we can get this video out to more people and keep doing well in calculus all term. So we will take these two numbers that we selected within this interval and plug it into our second derivative. So that's going to give us -1 is going to give us -6 times -1. +1 is going to give us -6 times +1, which is going to give us +6 for x equals -1 and -6 for x equals +1. So again, just like in the last part where we were looking for increasing and decreasing, when we're looking at concavity and looking at what output we get from plugging in these numbers into the second derivative, we don't really care what the specific number is. What's important is whether it's positive or negative. Since our second derivative is positive within this interval, that tells us that our original function is concave up. It's like a smiley face, right? It's curving upward. Because similar to how the first derivative of a function tells you about the slope of the original function, the second derivative of a function tells you about the concavity or the curvature of the original function. So if we know the concavity is positive, that means it's curved upward. So that tells us that our original function has an upward curve to it. Here we got a negative number as an output for our second derivative. That tells us that our original function is curving downward. It's concave down. It's basically like a frowny face shape. Okay. So our original function is curving up over this entire interval, and it's curving down over this entire interval. Okay, so that tells us our intervals of concavity are going to be concave down from 0 to +infinity, and it's going to be concave up from -infinity to 0. So these are going to be our intervals of concavity, okay? And then our inflection point is just x equals 0. Thanks for sticking around to the end of the video. If you did find this video helpful and you like getting good grades in calculus, go down below and hit that subscribe button and that bell icon too so you're notified when all my new videos come out. And we'll keep crushing it all term long in calculus together. If you want to keep this brain train rolling and keep on learning about some other topics of calculus, just go ahead and click on one of those videos over there and let's keep on going. Thanks and see you next time.